Thank you once more. Thank you for joining the call. You're welcome to this event. Um, in today's session about AI for startups, we will be discussing how we can build sophisticated AI models in 8 weeks. My name is Joseph Itopa Abubakar. I'm a machine learning engineer at Omdena with experience from projects across three diverse areas of application, which includes health, education, and environment. Today we'll have a little introduction about Omdena for those who are not aware or who are not informed of what Omdena is. It's just a brief description, and we'll introduce the guest of today, um, who will be talking about building machine learning model to identify trees, a project by SpaceX in partnership with Omdena, and welcoming and overcoming data challenges to predict malaria breeding sites is also another project from Zzapp in collaboration with Omdena, after which there will be Q&A section.
During first few days, it was burning the equivalent of more than one football field every second. 68 million tons of carbon dioxide were released to the atmosphere, equal to the 15% of California's total annual emissions. And according to experts, there's an undeniable link between climate change and wildfires. Rising temperatures, droughts, make fires more frequent and dangerous. But what caused campfire directly? Investigation revealed that campfire had two ignition points. Both of them were sparked by poorly maintained sections of power lines that came in close proximity to trees, which in turn hit and damaged the line during a storm. And the question is, how could that happen? Traditional ways of infrastructure inspection using helicopters, drones, walking are inefficient and expensive. But apparently, there is a way to do it cheaper, more frequently, and on a much bigger scale. The company called SpaceX had an innovative idea to monitor areas around utility lines from space, to use satellite images to alert about vegetation being too close to the power lines. Their idea is shown in the picture presented here. On satellite images taken along the power line, identify trees or just a forest boundary. Using precise data about geographic location of power lines, you can visually identify the danger of a tree being too close to the infrastructure. So that's how they imagine the high-level building blocks of their system. First, acquire raw data, then look for trees in proximity to power lines, and in case of danger, alert maintenance groups. But for that kind of business to be efficient and scalable, it needs to be automatic, right? Human going over images looking for trees manually is a bad idea. So that's the moment where machine learning can potentially bring a lot of value. But SpaceX founders didn't know at that stage if that can be the case here, if machine learning can help them to automate tree recognition. They assumed it can, but they needed to validate that. So they turned to Omdena, which role was meant to deliver proof of their concept, an automatic engine to detect trees, the foundational block of SpaceX's system. For 8 weeks, 36 collaborators, AI engineers, data scientists with various backgrounds and different level of expertise from all over the world, were building machine learning model to identify trees. At the beginning, we brainstormed on how to phrase the problem, what are the possible approaches, some basic hypotheses and assumptions, which metrics to choose, and how to pre-process the data. So here you can see how the job was divided. It's a common pattern that many of us were involved in data annotation, but also pretty quickly collaborators took up different tasks and formed 4 dedicated groups to work on various AI models simultaneously. The crucial part of the solution was data annotation. 144 high-quality RGB images were provided by the organizer. For every image, we had to create corresponding masks or labels, as you wish. High quality of the picture allowed us to outline objects precisely. We were able to distinguish trees from bushes and even cut off shadows, as you can see on the exemplary image here. Since we decided to phrase the problem as a segmentation task, drawing polygons correctly was one of the, if not the most important part of the challenge. We were very strict about it, and that really paid off later. Next part of the process was to find the best AI model architecture. We tried various approaches, we studied a dozen papers, and we knew that we needed a model that is very precise at the edges, that handles distortions or uncertainty at the borders well. There is a pretty well-known unit architecture developed for biomedical image segmentation. It is based on the fully convolutional network, but its architecture was modified and extended to work with fewer training images and to yield more precise segmentations. Although basic unit is powerful for general segmentation tasks, here was not precise enough. So the team founded the deep unit architecture. Deep units operates with contraction and expansion sites and uses U-connections to pass high-resolution features from contraction site to the upsampled outputs, and plus connections to better extract information with less error. So the end-to-end pipeline that we created was the following. The set containing 144 original pictures was divided into 119 images and 119 masks for the training set, 22 images and 22 masks for the validation, and 3 images and 3 masks for a test set. Each image and mask were further cropped into 512 by 512 size patches. So finally, as you can see here, we got 576 pictures with slight overlap. And the deep unit had its basic configuration at that stage. And that architecture turned out to be the perfect choice for this problem. Running just 10 epochs, we achieved 94% accuracy on validation set with no signs of overfitting, as you can see here. Here's an example of predictions over one of the images in the test set. The mask on the right is our prediction. White regions denote trees and other vegetations. As you can see, the edges are a bit blurry, but overall, prediction looks pretty good, I would say. Here, different pictures and also quite decent results. Nicely identified trees, bushes, and other areas like roads and houses were properly excluded. All data that we got initially for training were from Australia, but in order to better test our model, we also got some images from Lithuania. We were surprised that it worked pretty well. Mask was a bit blurry, but the model was not misled by green grass, for example. Then we decided to use standard augmentation techniques. In this case, it was just rotating images, and that produced much bigger number of samples for us to use. From the original 144 images, over 4,500 of images were generated by cropping and data augmentation, nearly 4,000 for training, and around 700 images for validation set. That helped us to push the result above 96% accuracy. You can also see the sharp edges here, and the masks are clearly less blurry. And for Lithuanian images, it was also surprisingly good. Greater differentiation over shadows, the road on top here was clearly outlined, and the overall prediction was more adherent to the original image. And it was astonishing that the model was able to distinguish trees from their shadows, which, to be honest, provided a precision above our expectation. So to wrap up, in just 8 weeks, the team was able to successfully validate the SpaceApp's idea by completing the proof of concept and deliver the foundational component of SpaceApp's product, machine learning engine to recognize trees. So overall, we delivered carefully annotated datasets of 144 images, the end-to-end image processing pipeline, 4 most promising machine learning models with respective results, and state-of-the-art machine learning model with over 96% accuracy. And also, we provided them with advices for further development. That allowed SpaceApp to technically validate their idea and enter a new level. They could proceed with the development of the platform that processes high-quality satellite images of infrastructure, whether it's power lines, railways, or gas pipelines. And thanks to collaboration with Omdena, was able to automatically alert about trees and bushes in proximity to the power lines. And it's worth noting that currently SpaceApp's deep learning solution is accelerated by the European Space Agency and is trusted by NVIDIA Inception program. Thanks for listening to my presentation. And I wanted to say big thanks to the whole challenge team and special thanks to Leonardo Sanchez. And at the end, I just wanted to encourage you to keep in touch with me, maybe. If you wish, you can find me on my website, aifortheplanet.com, via LinkedIn, or you just drop me a message if you want to connect and build something nice on my email. So thanks a lot once again.
You're welcome, Lucas. That's a great presentation. Thank you for that. You've really presented well. At this point, over to you, Lucas. Tanmay Laud, it's your turn.
Yeah, thanks, Joseph. Let me just share my screen. Okay, I'm guessing you can see my screen now. Okay, hi guys. So I'll be talking about the malaria project, reducing malaria in specifically the African subcontinent. This was a project that we undertook between August and September. But before explaining what we did in the project, I just quickly wanted to go through why we sort of why this project and why is the startup Zzapp trying to solve this problem. So yeah, so Zzapp, as a startup, is based in Israel, and they are basically focusing on the African continent, but definitely going to move towards the Indian subcontinent as well. And it's basically because these regions are currently more susceptible to malaria infections, and the cases are rising year by year. Given the current COVID situation, people might be not be worrying about malaria, but it's still there. It's taking 450,000 fatalities annually. And there's a huge investment going, in order to solve, for treating malaria cases. But Zzapp is trying to provide a preventive measure. So let me just quickly tell you how Zzapp operates in these regions. So the Zzapp approach, right? So Zzapp, what they are trying to do is they first basically divide a particular region of interest into 100 cross 100 meter chips. They are called MGRS chips, or the military grid system, because it's a standard system. And then they have their workers and volunteers going to each of these regions, and they try to survey the region and say if there is a water body there or not. But these are not any water bodies. These are specific water bodies that might be susceptible to breeding of malaria, breeding of mosquitoes that spread malaria. So they basically put that thing in the app, and then the app notifies them on their main dashboard. And that's how Zzapp collects data about the region. And then each of these workers have to basically go there and spray these water bodies with a particular organic chemical, so that and it's an organic chemical, so people can even drink that water, but it basically doesn't allow the mosquito larvae to survive. But why Omdena? If Zzapp is able to solve this issue, then why do they need artificial intelligence, and why do they need Omdena? The answer is that this process, as you might have understood, is very cost expensive and it's very time consuming, right? So expensive because the workers have to go and survey each of these regions. The app is involved. There's a whole infrastructure cost, human resource cost, and time consuming because they have to survey a huge region, and they have to do this specifically around the rainy season because surveying in the dry season is not the same as surveying during the rainy season, and that's when the peak of malaria infections takes place. So that's where our team of 40 collaborators from Omdena got together, from different places around the globe, and basically people having different expertise. And so that was the motivation. Can we pre-survey the area using computer vision and other data points, so that we can tell Zzapp specifically that this region has a risk of there being such a water body that can cause malaria infection. So so basically we're not just detecting river streams or just basically fast flowing water, because that is not susceptible to breeding of mosquitoes, but specifically ponds, maybe water collecting around the alongside the roads, maybe water collected on the terrace, somewhere in the tank, somewhere in the canal. So you understand that the problem is quite complex because these water bodies are not going to be directly observable by looking at a satellite image. Even though streams and rivers can be detected, these small water bodies that are around 30 cross 30 meters in size cannot be detected so easily. So then what are the challenges, right? So lack of enough data to work with. It's not like Zzapp or anyone did not have enough data to provide. It's the problem in general doesn't have much data online. There's not much public data set. There's not much effort going into that space. Although Zzapp is now started collecting data around that. But even if you have data, the whole public satellite imagery that's available, the resolution is not sufficient to be able to detect water bodies. Aesthetically, the images look good, but we do require a much higher resolution to detect the very small water bodies that are 30 cross 30 meters in size or smaller. Then the risk of missing a water body is quite high because if we tell Zzapp that this grid does not contain water when it actually did, then we are basically not chemically treating those water bodies. Next is there are various data dimensions that we need to consider, because since we are going around the landscape, rural areas have different kinds of features than the urban regions. And again, the seasonality comes into picture. Just if we survey, like if we apply computer vision on a region during the dry season, we are going to get the wrong results, and the results are not going to match when the season is rainy. So we need to basically generalize our models to different regions. Then there are different kinds of water bodies. So there'll be basically natural sources of water, like small ponds and lakes, and water collecting in the parks, let's say, and gardens. But it's different from how water can collect on a terrace. So artificial water bodies and natural water bodies, we need different features. So topography and terrain can deal with natural water bodies. It cannot deal with artificial water bodies. So we basically set out and created a pipeline for us, where we had the task one, which was around image processing, followed by annotations, and then we had two different types of imaging. One was direct imaging, where we actually look at the satellite image and try to analyze the features, and also indirect features like other than the satellite image, which I'm going to talk about soon. And then we combined the efforts of both these tasks into the final task of creating a consolidated output map for Zzapp. But today I'll only be focusing on task one. And the reason is, mainly two-thirds of our project actually went into data sourcing and collection. One, because it's a lengthy process, and two, we had to ensure that the data is in the correct form, because otherwise the models are not going to be useful. So, that's the reason two-thirds of our project was mainly data sourcing, pre-processing the data, getting the data in the right format. So let me just quickly go through the data sources that we used for this project. So we used something called a Google Hybrid Satellite Service. Then we used the population density metrics of the region. We used a land cover net data set. We used vegetation indices, and we used topographic variables. So let me go through each one of them and why we used them. So the Google satellite hybrid. So basically, if you look at the images above, these were given to us by Zzapp, and and what we did was we found equivalent images of those in the Google satellite hybrid, and you can clearly see a jump in the resolution. So for example, in this second image, we are able to separate the tree from the shadow, and here you can see we are able to identify the dwellings better. right? So this allowed us to basically get a better accuracy when it came to modeling the risk maps. Next was population density. So there's a research basically that the more the population density of the region, the closer is the distance of the land to the nearest water body. As you can see that as the population density is increasing, the land distance to water on the x-axis is decreasing. So that's why we basically took out population density of a region, and although we took the population density which was, let's say, 2 years or 3 years old, the idea is that the distribution stays the same even though the population of a region always increases. Next was the land connect data set. So this was a very special data set because it was curated by a team called Radiant ML, and it's specifically for the African continent, where they performed a combination of manual annotation and some machine learning to basically classify each pixel into these classes like trees, cover areas, shrubs, grassland, cropland, vegetation, lichen, moss, bare areas, built-up areas, snow, and open water. You will ask why not just use the open water from here, but the idea is that another research says that mosquitoes breed more in water bodies that have vegetation. So that's why things like vegetation, tree cover, all these things become more important when we are detecting water bodies susceptible to breeding of mosquitoes. Next was the vegetation indices, because following the similar approach that we need to detect vegetated water bodies, vegetation indices is basically some metrics that are applied on the satellite images to be able to understand by certain bands of the satellite image whether there is vegetation in that region. If you can see the red and green, the green part is sort of indicating a high vegetation and the red part means lack of vegetation, and that sort of is comparable to the image below it as well. And last but not the least, we had topographic variables. So this data was specifically included so that we could identify the natural water bodies better, because so one, we could detect natural water bodies, and also we could detect a possibility of future occurrence of a natural water body by the topography. So since we were scanning the region right before the wet season, it means that although there's no water body there right now, there could be in the future. So that's what topography allows us. High chance that there'll be a collection of water body there, right? So that's where the things like topographic variables helped us a lot. And this is the final pipeline that we got. So basically what we provided to Zzapp, if you look at the first square box, is like we provided a proper extraction pipeline to them. So it's like a pipeline that basically just takes the data from the source. So you need to provide the region coordinates, and we will go to all the data sources, collect the data, process it, and provide it to the models that we had created for Zzapp. So basically whenever now Zzapp goes to a new region, all they have to do is provide the region of interest, and our pipeline will curate the data for the models that we had pre-trained for Zzapp. So that's was our deliverable for Zzapp. And how we validated. So we had to employ a different kind of validation strategy, because when it comes to this kind of water detection, there's a high chance of correlation between neighboring regions. So we cannot just randomly sample and split the train and test data set. So we actually had to train on a completely different region. So we trained on West Obwas in East Amhara regions and tested on East Obwas in West Amhara. So completely split out regions. And these are the results that we got. So if you compare, so on the right I have the predicted labels, and on the left I have the actual labels. If you compare the right to the left, you'll see that the yellow part is more. So yellow is basically the the boxes where we detected water or the risk of water. You'll see the yellow in the predicted side is more. So this means that basically we sort of over predicted the regions having water. But like I mentioned earlier, there's a high risk of missing a water body, and it's okay to say that a region has water rather than saying that the region doesn't have water, and we being wrong in that case. And that's how we have basically tuned our models, so that if when we are confident about a region, we definitely say that there's no water body, but otherwise you will see a slightly higher water prediction. And what are the next steps? So, basically integrating the risk maps that we provided into the Zzapp platform. So on the right, you can see the Zzapp platform. And we would have to retrain these models once we get more label data, because these models that we trained were specifically for two small regions of Africa, namely Obuasi and Amhara. Next was experimenting the effect of things like climate data and transportation grids. Because these two sources were something that we actually provided to Zzapp, but since because of the 8-week schedule, we basically and also since climate data has a lower resolution, we have provided them as a pipeline to Zzapp so that they can in future even train based on these data sources once they have more regions to cover. And the last part would be a time-based analysis that Zzapp could perform. Basically, like I mentioned, from the dry season to the wet season, there can be a change in the occurrence of water in a region. So performing a time-based analysis will, let Zzapp know when exactly to send their people out for a survey or for, the treatment of water body. And with that, I'd like to end this presentation. So thank you for listening, and you can definitely ask me questions. These are the places where you can contact me, and you can definitely ask Q&A in the chat as well. Thank you. Thanks a lot.
Thank you, Tanmay. Nice presentation. I believe our audience were engrossed in the presentation of that Lucas and you have delivered. We have a question here, though the question goes directly to Lucas. The question is from Vikash Kumar. He said, if there are more than 20 trees in a single picture and overlapping happen with each other, then how do you go about the labeling in that situation? Lucas?
Yeah, right.
You understand the question? Okay.
Yeah, that's a good question. That's a good question. So we frame the problem as a segmentation, as a segmentation task, and there's to identify separately trees. You should go for instance segmentations. So we didn't really care about single and separate pictures of single and separate trees. We cared about just the border and the edge of the forest, right? So if we were to identify separately trees, we would definitely have to go for some maybe other architecture and other way of labeling that. But that wasn't the part of our interest. So we had to just identify the border, and that's it.
Okay, and okay. I hope you're clear. The questionnaire, or will I say the person that asked the question, Vikash. I hope Lucas has answered you clear. Lucas, one more question for you before I switch over to Tanmay. There is this other question here that said, what should the minimum number of images what is the minimum number of images required to get 95% or more accuracy over a test data set? That's for your project.
Right. So as you saw in our project, we reached that accuracy very quickly, and it was still very little number of images. So I don't know. I cannot recall the tests where we tried with different number of pictures. Right. We just used all that we had, and this kind of accuracy was reached pretty quickly. In general, it's very data dependent. How fast can you reach it? And I'll just give you an advice to be very careful about labeling. It's crucial, the proper labeling and being very accurate about proper polygons drawing is the most important stuff, right? So the better you draw the polygons, the less pictures you need. Less.
Thank you for the concise answer, Lucas. Thank you. Tanmay, there is a question here regarding your presentation. And the first one is, what are the modules you explored before finalizing the deep unit?
Okay, so I mainly focused on the data sourcing here, but we used around 7 models, for our project, and they were basically doing 7 different tasks actually. Just to briefly tell you, so basically were detecting water bodies using a deep water map that allowed us to detect the large water bodies. There were, for topography, we had to use another kind of a model. Then for the land cover net we used the unit, like you mentioned. And so basically we had 4 other such models for 4 different kinds of features, and then after that we created the meta features, that is the output of these models. We ensembled that using a final custom model.
Thank you. Another question for you. First, it is about after training the data, if we get more images, do we retrain the model? Do we retrain the module again? That's the question. And it was followed by, what was the accuracy of your best model?
Yeah, thanks. Okay. So basically our models were, just to answer the last part, the models were trained for a higher recall, right? So it's not just about accuracy, like I mentioned, it's about getting, it's okay to over predict, but it's to make sure that we do not miss a water body. So it depends on what you want to achieve. Regarding retraining, good question, because since, like I told you, we had 7 models, out of which a few were deep learning models. So when we had the deep learning models, it's okay to not retrain it, but rather just fine tune it on the new data set. But the final ensemble model was a basic, a machine learning model. It wasn't a deep learning model. So you would have to retrain that ensemble model after you fine tune your individual deep learning models. Thanks.
Okay, thank you for the answer. So at this point, we don't have any more questions from our audience, and we thank everyone for participating. Okay, before we go, I think Marvin just dropped a message. He said, kindly elaborate on some of the best sources for satellite images for similar projects. And Tanmay, I think that's for you.
Yeah. Yeah, nice question, Marvin. So basically, the Google Earth Engine is a really good, system. I would say it's not just a source; it's basically a framework that's going to allow you to get the satellite images, from various different data sources like NASA, Landsat, and so on. So basically, using Google Earth Engine is what helped us to get all sides of different data sources, and also to enrich the image resolution, maybe you can try the Google Hybrid Satellite wherever it's available.
Thank you for that. And I think, okay, how do we part of such projects in the future? Okay, this question is not for you, Tanmay. For future projects, I think Łukasz, you can kindly apply through the website, and just go to the website and apply omdena.com. You will see projects. Go under the projects tab, and then click on it. You will see the current challenges and the upcoming challenges. Go to the upcoming challenges and ensure you okay, thank you, Lucy. She just dropped a link, so you can follow the link and of course apply for the upcoming challenges. Thank you very much. Thank you, the audience. Thank you, presenters. You've done a great job today, obviously, and thank you for your time. I think
Joseph, I think we have a few more questions. Do you want to go through them if we have time?
have a new question, rather. We have a new question. For both Łukasz and Tanmay, a fundamental part is the actual labeling and preparing the data. After that, choosing different model is very hard as well. How do you go about choosing the possible model architectures? Sorry, I was taking long. Okay. How do you? The question basically is how do you go about choosing the possible module architectures? So, Lucas and Tanmay, any of you can go first. It's for both of you.
Lucas, you can go first.
Can I go first? Okay, so basically, after qualifying the problem into a certain category, right? As it was like in our case was like semantic segmentation. We were just looking for solutions for standard solution for semantic segmentations, right? So we started with what we wanted to achieve, and then Googled the suggested solutions, right? And out of those most popular ones, we decided to choose a few and simultaneously check them. That's the power of Omdena, that many people are just can in the same time try different models, and then in the end we are meeting and comparing the results, right? And choosing the best one that actually won, and that's it.
Okay, Tanmay.
Yeah, just to add to that. So mainly it depends on the problem you're trying to solve. So for us, let's say when it was the whole detecting water bodies that lead to malaria, mosquito breeding, it's you need to first also focus on the research that has happened before. So basically you spend some time going through the research that has already been happening. That's how we found about population density, about the topography, terrain, because there have been research in the past that has suggested that those sort of features are useful, and that's how you come to know which models have worked in the past, and you build on top of that in such a project.
Okay, thank you. Lucas, you have a question. Though I think Tanmay has answered something very similar, a question very similar, but this is to you, Lucas. Nacho is asking, how do you measure accuracy when dealing with this kind of data and mask?
It was on the pixel level accuracy.
That is quite a short answer and is very direct. So I believe Nacho will love that.
So you're comparing the pixel by pixel, right? Whether it's correctly been classified or not. That's more descriptive answer. You're welcome. So understood, I think. Okay.
So one more question before we go, and the question is from Muhammad Ali. He is saying, okay, his question is for both presenter, how to find the data pre-processing and the MLD or learning resources to tackle satellite imagery task. So he is basically saying that how do you get the resources to handle the project in terms of data pre-processing and the learning resources. Of course, maybe possibly he's talking about research papers. You guys are in better position to answer the question. So he's basically talking about resources for data pre-processing. So please go ahead. Any of you can start first.
Tama, do you want to start now?
So I would say that definitely Google is there for all this, but depends on the problem. You should basically go and read research papers around the problem, and that's where you would basically understand which specific model you can use or what sort of data pre-processing you need to do, because it's not like a standard pre-processing that you need to do. It completely depends on what you're trying to find. For example, in case of Lucas, you're trying to find trees. We were trying to find water. So it depends on the use case, and then you try to find research around it. And if you're asking what sort of frameworks to use, Google Earth Engine is one, and maybe Lucas, you can share what you all had used.
Okay, thank you, Tanmay. Lucas, do you want to add anything to that, or it's okay?
No, basically, I think it's okay. Yeah, that's the way it is.
Okay. So we'll have a minute or so to wait for further questions before we close the meeting. So, okay, this question is for you, Lucas. Any suggestion on labeled satellites or drone image datasets? Thanks.
Good question. Nothing comes to my mind right now, but just drop me a message maybe, and I'll try to think of something. Maybe I'll point you to some resources. The data set that we labeled is not public, so yeah. But for sure, there will be something to share with you. Yeah, I'll find something.
Thank you for the answer. And okay, Antonio, he's saying, is Omdena financed by some third-party organization like NGOs or private company? No, Omdena is not funded by any third-party organization. So just to clear the air. Thank you. So we'll have a minute or so. If you have any further question regarding the presentation, so that we can answer it before we close the call. So while we have no other questions, thank you, Lucas and Tanmay, for your presentation and for the Q&A section. It has really been wonderful, and I believe the audience also love it. Thank you for your time, and thank you, the audience, for taking your time to participate. It's not easy, of course, and also thank you for making it interactive, because without your question, it will not be interactive. Thank you so much. Till next time, and do ensure to apply to Omdena projects or challenges. Bye, everyone.
Thanks a lot. Thanks a lot, everyone.